Thank you for inviting me. I'm assuming generally that you may not be familiar very much with knot theory and topology, and so I apologize if you are. The talk will be quite introductory, but it is about some research that I'm doing, and so we'll get to that. So the title of the talk, as you see, is entitled Knots, Vortices, Topology, and Reconnection. But as I said, I want to be introductory about how knots are related to physical things. And so I want to begin with a little movie that we made a long time ago, if I can get it up here. And you'll see what this is about if I can get it to work. There. Now, I don't know if the sound will come through. If it doesn't, I will narrate. Oh, it does.
The great physicist Paul Adrien Dirac devised a topological trick with strings in order to illustrate graphically an elusive property of the spin of the electron. In quantum mechanics, all particles are connected to each other and to every observer in the universe. For an electron, there is a quantum state or wave function relative to a given observer. If this observer should walk around the electron, making a full turn of 360 degrees, then the wave function changes sign. This means that while a quantum mechanical system involving electrons is not brought back into exact coincidence with itself after it is rotated by 360 degrees, it is brought back into coincidence with itself after it is rotated by 720 degrees. Here is Dirac's visual metaphor performed as the Philippine wine dance. Watch closely how the dancer winds the cup through 360 degrees, acquiring a twist in her arm. Then she winds the cup through another 360 degrees, and the twist in her arm has disappeared. Notice how the ribbon is moving around the inner sphere. The ends of the ribbon do not move. They are fixed to the respective spheres, and yet, now the ribbon returns to its original position and all the twist is gone. This is the Dirac string trick in modern form. We have programmed the computer to twist the space between the spheres. The strings, whether one or many, are located in that space and acquire their twist from the twist of the space. Once we untwist the space, the strings untwist as well, and we have given you a glimpse of quantum mechanical reality.
So now let me go back for a moment to the topological mechanics of that. There it is. Okay, and one more. So you're looking at a 720-degree twisted belt attached to the outer sphere and attached to the inner sphere. And as the movie explained to you, we're going to move the belt around isotopically without crossing through itself or anything, just like an elastic band. But it is rooted on the lower sphere and it is rooted in the upper sphere. That part doesn't change. It's glued to those spheres. And as you move it around, all the twist disappears and you end up with no twist at all. I don't have an animation here, but we'll do it with a belt of what happens if you had only 360 degrees of twist. But this is just simply a topological fact about the way a belt attached to two things will behave. On the other hand, Dirac pointed out that you could think that as a visualization of how it is that the sign of the wave function would change for a fermion if you walked around the fermion and came back to where you started. A 2 pi twist will take you to a minus sign in the phase, and another 2 pi journey will take you back to where you were to begin with. And then, did we give you a glimpse of quantum mechanical reality? That's a nice question, in as much as perhaps you could think of quantum mechanical reality as a world in which everything is connected to everything else by invisible strings. But that is not the way physicists have usually thought about it. So you might wonder, what does this have to do with what is going on? And if you know some quantum mechanics, you know that there's a different sort of explanation that goes on here. If you do, think about it for a moment. Well, the explanation is that quantum mechanical wave functions evolve by unitary transformations. And this was understood as a basic principle after Schrodinger and his equation, where it was understood that the quantum wave function evolves unitarily. But when you apply a rotation in 3 space to something, like rotating the observer around somebody, you're not working in the unitary group, you're working in the rotation group. And the unitary group, in this case, that's most natural to associate with the situation, is double covering it because of the fact that the rotation group, SO3, the rotations of 3-dimensional space, each of which is a rotation by some angle about a given axis, they form a group. It's double covered by the quaternions. It's double covered by SU2 or by the 3-sphere. Those are all equivalent descriptions of the group that it's double covered by. And I'm not going into the detail of that, but if you know it, then you understand from that point of view that as you rotate it around, you're moving in some unitary transformations. And by the time you came back to where you started, you're on the other sheet of the covering space. So what is being seen here is actually the fact that the fundamental group of the rotation group is Z mod 2, as order 2. And again, that sounds a little abstract, but if you think about rotations, then you can understand that that path, which I'm imagining now has a 360-degree rotation in it instead of no rotation at all, and I don't happen to have a cartoon for that. But if it did, then you could start at the bottom. You could start at the bottom, and as you moved up a little bit, you would turn this a little bit. And you would, by the time you got halfway, you would have turned it all the way around by pi, and that pi over 2, or no, by pi, I'm sorry. And then by the time you got up all the way up to the top, you would have turned it around by 2 pi. So I'm thinking of taking that interval, and as I'm moving it up, I'm turning it. And you see that what is being traced as you do that is the band. If I wanted to do 720 degrees, then by halfway, I would have turned it once, and by the other halfway, I would have turned it again, and I'd have 720 degrees of rotation in the band. But what was I just describing to you? I was describing to you a pathway in the group of rotations. I started with the identity rotation, and I moved along, and now I'm doing a rotation by pi over 2, and now I'm doing a rotation by pi, and so on all the way up. So this image here, this image of, maybe we ought to have an image of 720 degrees to talk about while I'm making my noises. Let's get the 720 degrees back. There. As I'm walking, oops, now how did that happen? Back.
No, it's back.
It's back. All right, anyway, as I'm walking up through here, I'm getting an image of a path happening in the rotation group, starting at the identity. And as I go up here, I'm rotating by a certain angle, rotating by a larger angle, rotating by a full 2 pi by the time I got to here, and then continuing and doing it all the way up to 4 pi, which takes me back to where I started. So this band is an image of a path in the rotation group. And when you saw this moving around, what you are watching is a deformation of that path. And there is a deformation of that path starting at the identity and ending at the identity, which takes you from the path which rotates through 4 pi and ends up with the path that doesn't rotate at all. That's the identity path in the group. So you're actually looking at a visualization that the fundamental group of the rotation group is the integers mod 2. You're looking at the order 2 element in the rotation group. So I think this is a very nice example, which we won't go into in more detail, but it's a very nice example of how topology in its raw form of being strictly visualizable things, or things that you can think about, does this deform to that, can be related to other subjects like quantum mechanics, and can be related to groups and many other things. So it's a very nice example to think about. And as far as I know, Dirac is famous for this trick, but he never actually wrote about it anywhere. So that's a curious fact about this example.
Can I ask a quick question?
Question?
So you realize this element as an element.
I'm sorry, I'll probably have to come near you to hear you.
Sorry, I could have approached you, but I think that ceiling mic is on, so you don't need to worry about that. So you articulated a span as an element of order 2 in the rotation group.
Not the band. The band is an image of the element. It's an image of the square of the element of order 2. The element of order 2 is a path in the group, which starts at the identity and rotates around, and it goes through rotations. So at any given time, it's a rotation by some angle. And at half time, it's a rotation by pi. And at full time, it's a rotation by 2 pi. That's the generating element. This is the square of it. It's a rotation by 4 pi. And you're looking at an image of the path. And then when you see the band deform, you're looking at the homotopy to the identity.
But does every element of order 2 in the rotation group have such a geometric realization?
It's not the elements in the rotation group that I'm talking about, but the fundamental group of the rotation group. So that every element, well, let's go back to the rotation group. The rotation group is very simple. It consists in choose an axis and choose an angle of rotation and rotate around that axis by that angle. Then, of course, if I defined it that way, you have a nice puzzle. How do you prove that given a rotation around this axis by an angle and rotation around this axis by an angle, if you compose them, there is a new axis and a new angle. But that's a fact. Okay, so it forms a group.
Yeah, I'm happy with the group structure of the rotation group.
Mm-hmm.
But when you look at the elements of order 2, you seem to be looking at the elements inside the fundamental group.
Yes, I'm looking at the fundamental group, not elements of order 2 in the group itself. I'm looking at a path on the group.
You're looking at a path on the fundamental group.
No, a path on the, there are two, oh, I see. There are two groups here. There's the rotation group, but I'm thinking of the rotation group like a space.
Yes.
And then there can be paths on that space.
I understand.
And let's back up for a moment as long as we're talking about this. What kind of a space is the rotation group? Well, you can think about it. I would like to create a picture of the rotation group as a whole. All right. So what I'm going to do is I'm going to take a ball of radius pi, and I'm going to associate to the origin the identity in the group. But if I go away from the origin, then I'm gone away from the origin by some direction, and that's going to be the axis of rotation. And then if I go along the radius from the origin, I can mark an angle on that line up to pi or down to minus pi. And that angle will be the angle of rotation, because a rotation of pi is the same as a rotation of minus pi. So that means that if I take a ball and I take a point in that ball, I can say, how far are you from the origin? That's the angle. And what axis is that going through the origin? And that's the axis. And it gives me a unique rotation, choosing a right-hand rule for things. However, out at the boundary of the ball, the rotation by pi is the same as the rotation by minus pi, which means that antipodal points on the boundary of the ball have to be identified with one another. And then I get the topology of the rotation group. The rotation group is the three-dimensional ball with its antipodal points on the boundary identified with one another.
You take a quotient of your...
That's right. And it's that space whose fundamental group is the integers mod 2. And the reason why is because there is this loop, which if you take in the ball that I described to you, if you start with a point on the lower, on the South Pole and run all the way along the axis until you hit the North Pole, that corresponds to a path through rotations that start by rotating by minus pi, keep turning until they rotate by nothing, and then keep on turning until they rotate by pi. It's a 2 pi, it goes through 2 pi. And the beginning and the end are the same because we identified the top and the bottom. That's a loop in the rotation group. And that loop, it really basically corresponds to the vertical direction in the geometry that I'm illustrating. Maybe that's more than you wanted, but
that was the term group and elements of order 2 per use are interchangeable.
Right. But if we're talking about the physics, then it's very interesting because we see that instead of the usual picture is that we don't take a fantasy, although you could perhaps take a fantasy of the world. It consists of not just localized particles, but particles, fermions, attached to one another by invisible strings that are tracking this topology. But we don't, but if you want to think of free space in the usual way, then the group theory, which is right next to the free space and telling you a whole lot about it, is telling you the rest of the story. So you might, whenever I look at it, I feel like they ought to be one thing rather than two things, but how you do that is a nice question. Okay, so that's the string trick, but maybe there's one more thing that's worth mentioning as long as we did that, and that is you can illustrate it with a belt, of course, and if Andriani would hold on to this right there, and we'd better stand side to side so people can see us. Just hold it in there so we don't use too much belt. So then I can illustrate what I was doing, right? I can turn this by, that's one full twist, and here's two full twists on the belt. Now this is the inner sphere, and she's out at the outer sphere. And I want to bring it around the inner sphere, but my arm is in the way. So this is not meant to be a sleight of hand. I'm going to exchange hands without twisting. And that's just as though my arm, it went through my arm, right? And then it can come around and unwind. So that's the trick, right? But this trick can actually, this trick can actually be performed in any direction in space. And I'll illustrate with my, what is it that I did that made that happen? Or did I? Oh, it was what you did. Right. If you turn the light on again.
Turn it up.
Yeah. You can illustrate it with your arm. If you think of this as this is supposed to be a belt going up to my arm and attached here, then I could turn the belt like I turned the belt buckle by 1/4 turn. I'm a 1/4 turn in terms of 2π, right? So if I make this turn, then I want to show you what happens. Now, what did happen with the belt? When you made 4/4 turns, you ended up with one. Am I saying it right? Half turn. I meant to say half turn. Sorry. This is a half turn because if I do it twice, I get a full turn. And that's as far as I can go with my arm, of course, in this direction. But I want to show you doing it around different axes. So one axis is the axis perpendicular to my body, and I'll call that I, and I can do one half turn is I. Now, why do I say I should be a half turn? Because I squared is -1, and the -1 is the thing whose square is equal to the identity. And the thing whose square is equal to the identity was the 2π, right? So from this point of view, I, as a half turn, acts like the square root of -1, where the square root of where the -1 is the 360-degree turn. Now, maybe we ought to come back to the 360-degree turn for a moment. Actually, that's sort of the geometrical secret of the thing. If I do a single 360-degree turn, then when I bring it all the way around the sphere, it won't come back to nothing. What will happen to it?
Stay fixed.
It comes back to itself? Not quite. Depends on how observant you are. It's twisted in the opposite direction. Maybe you want to watch that. This time it's twisting, it's curling from her to me, it's curling this way. All right. And now we bring it back around. And now from her to me, it's curling the other way. So that in a way is the secret of the trick, right? Because when you bring it a 360-degree twist all the way back around, it turns into the opposite twist, and that will cancel the other one. So, okay, so that's the -1. The 360-degree twist is the -1. So now I have the following. If I do this, I get -1, and that's I. But what about other directions? Well, there could be J. J will be across my body like this by 1/2 turn. That's J. And sorry, I always get my orders of things mixed up. The next one I want to do is J, and J is going to be around the vertical. So pardon me. I is this one, and J is around the vertical by 1/2 turn. And K is this one. All right. So now you see that if I do I and then I do J, it's the same as if I did K. And if I did K squared, I get -1. And if I did I and then I did J and then I did K, I would get -1. So you see what you're looking at if you're familiar with the quaternions. You're getting I squared and J squared and K squared are -1, and IJK is -1. And those are the famous equations for the quaternions that Hamilton wrote on the bridge in Dublin in 1843, right? So that's the quaternions. And so the belt attached to an object in three-dimensional space boosts the symmetry group of the object to a corresponding symmetry group of that object inside the quaternions. And that's the concreteness of the relationship between rotations and unitary group. Well, I've spent a lot of time on that, more than I intended, but I think that it illustrates a lot of things about the relationship between topology and its possible applications. So let's continue on now. And try some of this slideshow. I think we're good. Oh, it went away. Maybe it will come back. Yeah, sure. That's funny. It was doing fine before. Hmm. Ah, okay. Okay. So, so another aspect of things, we hadn't yet got any knots into the situation. And I tell you, this is also not a knot. Can you see that it's unknotted? It is unknotted. You don't have to turn the lights back on. I'm not going to demonstrate that this one is unknotted, but that's the problem with the knot theory, is that makes it something that people want to theorize about mathematically, is that if you have something which is knotted, like this knot on this rope, and if you say, either by closing the ends of the rope together so that you can look at how this object moves around isotopically in space, or if you say that you will not be allowed to slide it off the ends, then it won't go away, no matter how complicated you do various things in the middle. It won't. This simple one won't. But on the other hand, if you make a more complicated one, like this, it may still have the property that it's knotted, and then you can make it even more complicated and it's still knotted. And then maybe you do something like this, and it looks knotted, and it certainly does look to the eye as though it's knotted, but I'm not doing, I'm doing a magician's trick, but there's no sleight of hand in this trick. It just is unknotted. And how do you tell when some complex configuration in front of you is knotted or unknotted? That's the problem in the knot theory. And in order to solve this problem, it took a while for people to realize what they might want to do. I don't think people realized there was a problem until people started to think about topology. But by the time the 19th century was coming to a close, Poincaré, I probably have my history wrong. Poincaré had defined the fundamental group, which we were mentioning a moment ago, and people could start to think about loops in the complement of a configuration, a knotted configuration like this, and they could begin to prove things like of the non-triviality in some appropriate sense of the fundamental group of the complement of the knots, so looking at loops outside the knot. And this one would just have the integers for its group. You can, if you have an unknotted loop like this, you can go around that with other loops once, twice, 3 times, 4 times, any number of times. There's an integer group associated with that. But if you look at the same kind of structure and you think about it in relation to somebody like this, the group is more complicated. And so people began to understand, Max Dane and other people around the turn of the century, 20th century, that you could prove that different knots were different from one another, and that some knots were different from their mirror images, many other things by using the fundamental group. But this culprit here is unknotted. And you probably, unless you're very good at visualizing, haven't figured out how to unknot it. So I want to give you a clue and then we will go on. I won't do it. But if you're interested afterwards, I can show you how to unknot it. But there is a clue for trying to unknot things, which has nothing to do with group theory per se, just combinatorics of the diagrams. You look around and see whether there might be some arc in there, which if you were to move it under the diagram would make the thing simpler. And see this arc, it goes under 2. It's under this one and it's under that one. So it's going under 2. And if you push this arc under the diagram and around like that, these two would go away, but this would wrap under there in order to connect it up. Everybody see that? So you could reduce the number of crossings in the diagram by 1 because there were 2 under and then there'll only be 1 under. That's significant, right? That's a good move. It doesn't show you, unless you're a very good visualizer, that move will win the game. But if the game is to look for good moves at a given stage, then that's obviously a good move. And if you look for moves like that, you probably will manage to unknot things that are unknotted. There might be a conjecture in that. I don't know how to formulate it for general diagrams so well. There are many other ways of representing knotted or unknotted configurations. Here's an ordinary trefoil knot like the one I had on the rope, but it's made out of straight pieces of iron in 3-dimensional space. And here's a link, the simplest topological situation that we can think about. And if you have a link, then there's a very simple way of getting some topological information about your link. Namely, count how many times one component goes around the other. And you should count it correctly. That is, if it goes in, then it came right back out. You should count one as plus and the other as minus. So of course there's an algorithm for doing that, but I'll skip it. Here's an example where linking number isn't good enough. These are the Borromean rings, very famous rings, and they're linked. You can't pull them apart topologically, but there's no linking number between any pair of them because, for example, green goes in between blue and then comes right back out. There's no counting of linking, of going around. Green does not go around blue. And if you were to remove green, then red and blue will just come apart, and that's true of any one of them. So they're linked as a triple, but no pair of them are linked. So there are lots of questions of this kind. Here's the trefoil knot again. And in this case, I wanted to give you a hint without going into the detail. So I've colored it, or the picture is colored. Maybe I didn't do this picture. It's colored in 3 colors in such a way that the things that are colored are the arcs in the diagram. So I'm starting at an undercrossing and walking along until I get to another undercrossing. And then I'm meeting blue and I have to change my color and I become red. And then I'm meeting green and I have to change my color and I become blue. And this is a 3-color system, so it ends up getting colored in 3 colors in that way. And the rule for coloring that I'm going to follow, but I only give you the hint, is that you must at a crossing have either 3 colors like this or 1. And you can imagine that this made a little loop here and then it would be red meeting red and red comes out. 3 or 1, never 2. That's a rule. And if you follow that rule and try coloring it after you pushed it around a bit, you'd find that you could still color it. And you'll find that whenever you have any picture of the trefoil knot, it can be colored with 3 colors. And so the 3 colors are a characteristic of the topology of the knot. And by dint of thinking about that, you can prove that the knot is knotted. It's a little simpler than working with the fundamental group. So now we arrive at another cultural matter. Before people started to do mathematics with knots, they were doing lots of things with knots, practical things with knots, of course, but also decorative. And Celtic knot patterns are characteristically looking like this, according to Mr. Romilly Allen, who wrote this book around the turn of the century. That his thesis was that the main way to make Celtic knots was to take a regular rectangular pattern like this and then modify it by taking a crossing, a weaving crossing in the pattern and replacing it in such a way that there was no crossover. And there are 2 basic ways to do that, as you see in his diagram, like that. Okay? So that's a part of the lore of Celtic knot tying. And if you go looking up Celtic knot tying and production of Celtic knots on the web, you'll find some programs that let you do that. You'll have a square lattice like that, rectangular lattice, and it will let you change the crossing and produce patterns. Well, it's very amusing and interesting to the knot theorists to see that, because at least I wasn't aware of this at all, this idea coming from Celtic knot tying, but the idea came through, and around 1985 or so, it became clear that you could try to make invariants of knots by using the same idea. So that goes in the following way. You have a knot diagram. I'll show you an example in a moment, but you have a diagram for a knot, a drawing of a knot, and then you can make 2 new things associated with it, one of which may be a knot and the other may be a link. But you can do that just like Romilly Allen did for his Celtic knots. But then instead of thinking this one's a better pattern than that one, we take them and add them up with some coefficients. And then it turns out that if you do that until all the crossings are gone, adding up, you get a polynomial in A and B, and then you can have another variable for the loop involved. And if you adjust the coefficients correctly, then the resulting polynomial will be an invariant of the knot, in the sense that if you move the knot around topologically, it'll give you exactly the same result after a little bit of normalization. And furthermore, this way of summing up is related to statistical mechanics models. It is a kind of statistical mechanics model on the knot diagram. So the way this looks, if you did it in practice, and I'm putting the details of getting the coefficients right under the hood, but there they are. When you smooth it one way, you multiply by A, and when you smooth it the other way, you multiply by A inverse. But what's more interesting is the diagrammatic geometry of it. You see, here's the trefoil, and I decided to do that process here. So I smoothed it this way, and I got a link. But then I smoothed it the other way, and I got an unknot with some curliness in it. And then I'm looking at this one, and I smoothed it this way, and I got an unknot. And I smoothed it the other way, and I got an unknot. Now I know how to evaluate each of these by the method that I'm using. I know how to evaluate curly unknots. And the curliness is kind of a measure of the helicity, at least of the curly part, so that it is though the knot fell into 3 in this case, and it would be more in general, 3 helicities that I'm measuring, and I'm adding them up. And when I add up these helicities, there may be a kind of tendency to have helicity in one direction versus another. I had to normalize it, having to do with the crossings themselves. And by the time I had normalized it, the helicity is all gone south. You see those negative exponents, so that it's measuring the fact that the knot is winding very much in one direction rather than the other. And topologically, this polynomial doesn't change when you move the knot around in space. And so we end up proving by using this method that the trefoil knot and its mirror image are distinct from one another. You can't transform one into the other. You have topological helicity. That's one of the things that that we have understood for a long, long time about knots, is that sometimes they're equivalent topologically to their mirror images and sometimes they're not, but we don't always have good ways to prove it. This is a very simple way to verify that the trefoil knot is helical in that sense, or chiral. But this chirality is worth comparing with what happens in chemistry and other circumstances, where the chirality is often more geometrical than it is topological. You have a helical molecule and it's winding in a given direction. You're not thinking so much about maybe it would be smoothing itself out and into an unwound thing and then winding up in the other direction. It just geometrically happens to be winding in a certain direction. So there's geometrical helicity, but this is topological helicity. And that's very interesting and subtle. And maybe we ought to take a moment and illustrate it. Let me show you an example where something isn't equivalent to its mirror image. I'm sorry, where something is equivalent to its mirror image. So what I have here, if you can maybe turn on the light. What I have here is a figure-8 knot and its mirror image. So it can have a mirror image. It seems to have a geometrical mirror image. But this acts a little like the way you can turn a left-handed glove into a right-handed glove by turning it inside out. But it's not happening by turning it inside out. It's just happening by pushing it along the rope a little bit. So I take the right-hand one and I give it a little push like that. I might have pushed it too much. I have a feeling I did too much. And we're back where we started. So we'll do it one more. I think you're not going to believe me. Let me try one more time. There. There. No. No, they're not the same. Maybe I should hand it over to Andriana and she'll So try one more time. The point is that all you have to do is roll it once over itself. And if you roll it twice, of course, you end up back where you started. And I'm not being very good. Well, I'm not being very good at it, but I'm going, so I'll let it go. We can do it later. But maybe maybe another way of showing it would be helpful. Let me show you that. So here's one figure 8 knot. Let's try this. The reason I went to this rope is because I can plug it into itself. Like that. Okay. So it's a closed loop. And then here's the figure 8 knot. All right. Now, let's make another oh, I don't have another plugged in. So you just have to remember which way it looks. But the idea is that we're going to swing this arc around like that, no more and no less. And then I see this needs more practice. One more try. We have a blackboard? No, never mind. I take this as an instruction to try to do it. You could draw it out, draw a picture of it. What you're looking at this, and you want to think of this guy here as now surrounding the entire thing like this. And now you're looking at another version of the figure 8 knot. But by the time you've done that, you'll see, but that's what's not working so well here. You'll see that you've turned it into its mirror image. You've turned it into its mirror image by taking that arc and bringing it all the way around. And so in any case, some knots have a definite mirror image, but it's only geometric, and topologically they turn into their own mirror images. So where are we? We're coming near the end of the time, and I didn't get to telling you about vortices very much, so we'll do a little. You see that this method by which I was explaining how to get knot invariance by opening up the crossings in the two different ways. If you had a given knot diagram, there are going to be 2 to the n different ways of opening it up. And so you get a big collection of things that have to be summed over. And when you sum over them with the right coefficients, you get a knot invariant. And that gives a model for the well-known Jones polynomial. And it can be studied in this form very usefully. And another idea that came through in the late 90s was from Kovanov, who said, well, this collection of states that you're summing over forms a category. And the simple idea there is that if you have an A type, if you have a smoothing of one type and you change it to a smoothing of the other type, then there's a directionality to that. So if you put a directionality into the way you smooth from one type of smoothing to another, then you get a structure with arrows, which is all a category is, basically. And then thinking of it as a category, one can ask, how does the category change when the knot changes, when the knot moves around? And how do you measure from the category how the knot changes? And it turns out that you can define a homology theory associated with the category that will measure how the knot changes, and that's called Kovanov homology. So there are higher order invariants that are related to the invariant that I've been talking about. And we aren't going into that, but it is in back of what I'm going to talk about with the vortices, which we'll do quickly for a few minutes. Now, knotted vortices are an old idea. Lord Kelvin suggested that atoms in the luminiferous ether were knotted vortices in the ether. There was the notion of a pervasive fluid, and that you could think of vortices in that fluid, and those would be the atoms. And that was his a theory, and a very popular theory in the 1900s. And what came out of that were the beginnings of investigations of knottedness in fluids and vortices, and the theory itself, of course, came a cropper because people no longer thought of the background space as being a fluid that could have vortices in it. But he started something very interesting in doing that. But no one had ever seen a vortex in a fluid. And no one did see a vortex in a fluid until around 2012, when Irvine and Kleckner produced a vortex in water. So everyone had seen smoke rings, and the people who were thinking about knotted vortices back in the 19th century, they were thinking about things like knotted smoke rings, but they didn't know how to produce them. And so here's the question which Irvine and Kleckner are asking. How can you produce a knotted smoke ring or the equivalent in water? And you know how to produce a smoke ring. You blow the smoke across your lips, or you take the equivalent of lips, a circular object like this, and pull it back quickly through the water, and you will get a vortex coming forward. So they made a knotted framework. They made a knotted template. Here's a template that will produce an unknotted vortex. And down there in that slide at the bottom is a knotted template. And they used a knotted template to produce knotted vortices. And here's the illustration. Here's their film of an unknotted vortex. And here's the film of the knotted vortex. Now, when that knotted template moves down, the vortexing occurs along the upper edge. You're seeing it here in this frame. And you see that, of course, it's a ribbon of vortex, but it's only the forward part of the ribbon that has any stability at all, or not a whole lot, but a lot more than the intermediate part. And so as time goes on a little bit, you get this coalescence at that edge, and there comes your knotted vortex. And this knotted vortex is not very stable. It tends to come together at some point with itself and cause itself and destroy itself. But it destroys itself in a very interesting way. It destroys itself like this. It comes together, goes through a complex interaction, and ends up getting the other smoothing. It's like our category of going from the A-type smoothing to the B-type smoothing, or in any case, from some type of smoothing to the other type of smoothing, to the other picture in Romilly Allen's picture. And it tends to do that whenever it gets close to itself in the appropriate way. What's the appropriate? Now, I'm being careful here, I hope, about time. That's one way of modeling. I'm digressing for a moment. Another way of modeling is by using a nonlinear Schrodinger equation and having the vortex be the place where the phase has the phase. There's the phase in the solution to the the phase up there, phi. Phase is undetermined. Those places are the vortices. And then you can do computer modeling, and you can see this reconnection phenomenon going on like that. But we were saying, when is it favorable for something to happen? It's favorable for something to happen if you think of the fluid flowing, when the fluid is flowing in the same way in between the two bits of vortex that are coming together. And you see that that's illustrated here. The flow is away from the board, away from us on the left, and the flow is away from us on the right. But that means that this is rotating counterclockwise from your point of view, and this is rotating clockwise. And so I could indicate that by putting an arrow on the line, which says by the right-hand rule, you're rotating that way, and by the right-hand rule, you're rotating this way. And then I think of orienting the line. And then if I have a knot, for example, and it's got rotation going around it, it's a knotted vortex, then when these two edges come near one another, they're favorably rotating in such a way that you might get a reconnection. And you do, in many cases, get a reconnection. If you did get a reconnection, you would start here and you would end up here. And that's a link. So you're not completely unknotted, but the link could interact with itself, for example, here, and then you'd be unknotted. So that leads to the question, which I was going to start the talk with, but I'm ending the talk with the question and then telling you one or two things and we're quit. The question is, if you had a knot and you were going to allow it to reconnect, then how many times do you need to reconnect in order to be sure you've got an unlink, you've got an unknot? How many reconnections do you need in order to unknot the knot? So it's similar to a more well-known question about knots, which is how many crossing switches do I need to make in order to unknot the knot? But if you're watching the dynamics of reconnections of vortices, you'd like to know how many times did it really have to do that? Well, I'll run through some examples quickly. We'll skip this movie. And I'll come back to that four-dimensional idea. But here's a knot. And when we did an experiment with it, it happened this way. It reconnected here, turning into a link, and then it reconnected, turning into a trefoil knot. And then the trefoil knot, of course, disappeared after two more. So it looked like it took a number of reconnections to disappear. But on the other hand, that knot can be unknotted by switching one crossing. So you might ask, what's the relationship between switching? Do you see that? If you switch that one crossing there, here's the original knot. If you switch that one crossing, then you see that thing is actually unknotted. Just slide it over to here, pull that way. It's gone, all right? So maybe you could do a switch of a crossing using reconnection, and you can. And it only takes two. See? This is strictly what a topologist would think, because many of these steps are not necessarily what any physical system would want to do. Topologically, you can put a little curl here, then these are going in the opposite direction so they can reconnect. having reconnected, this can pull under, then it can push over the top and reconnect again, well, then get rid of the little curl. And so if I think of starting here if I think of starting here with this going over like that and ending here, then I've done it, and I've done it with two reconnections, right? So two reconnections can effect the switch of a crossing. And that means that in some strange ideal world, this 6-2 knot could undergo 2 reconnections and become unknotted in just the way I was telling you. The curl interacts, this pulls out, comes back over. You do another reconnection, it's unknotted. So now the question is, now there's a pure mathematician's question. How many reconnections are needed? And so I'm going to jump to an answer in one case, one general case that's amusing. I'm skipping through something. Let's take this. All right. So this is a formula for the reconnection number of a knot where all the crossings are positive. And I didn't tell you what I meant by a positive crossing. It's very simple. I'll tell you in a moment. And the formula says you take the number of crossings, you subtract the number of so-called ciphered circles and add 1, and that's the reconnection number. Now, the best way to illustrate this might be, since we're wanting to do this not in a large amount of time, is to show you what I mean on this diagram. This is a positive knot, a complicated one. Positive just means that every crossing follows the right-hand rule. If you put your fingers in the direction of the overcrossing line, your thumb points in the direction of the undercrossing line. Not every knot is positive, but infinitely many are, but they kind of rotates always around itself in the same way. The ciphered circles are obtained by smoothing the crossing in such a way that it's oriented after you smooth it, see? Like that and like that. That's what I did there. And I smoothed every crossing so that it was oriented. That means that the orientation of the entire assembly is inherited by all these circles, and those are called the ciphered circles, okay? And then it turns out that you didn't really need, if you were trying to do reconnections, because every one of those smoothings could have been done by a reconnection. You can, if you reconnected, then what would have happened is, instead of just smoothing it, you'd have a little curl. But we're only interested in the topology, so we can forget those curls. So that means that what I got here was an unlinked thing, which was made up out of doing 1 reconnection for every crossing. Okay, but I didn't need to do that many. I could chain these all back together and not do them. And if I did that, undone, 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 some are done, then the ones that I don't need to do is equal to 1 plus the number of circles here, because I'm chaining all the circles together. 1, 2, 3, 4, right? 1 less than the number of circles there. I don't do it there. I just do the reconnections at the other places. And so I end up using that many reconnections, the number of crossings minus the number of circles minus 1. That'll do it. But how do you know that's the least? Well, that's where you need to use the Kauffman homology, and we aren't going to touch that here. So this is a good place to stop.
Thank you so much. Is there any questions?
So when you use the Kauffman homology, how?
Sorry about that.
No, sorry. So, when you use the Kauffman homology, you take this number, is that the dimension of the homology? What kind of information do you take a number?
Well, there's a shaggy dog story there. What I didn't mention for lack of time was an important idea, which changes the geometry of the way of thinking about it, but it's a simple idea. If you had a knot and it underwent a reconnection, then you could think of a surface being generated in space-time, right? Because when you undergo a reconnection, then you start with two arcs that are like this, perhaps, and then you end up with two arcs that are like this. And what I just generated here, let's start here. This is the waist of my pants. And then I go through and do this. Now I have the pants themselves. And this whole surface is a pair of pants. You went through a saddle point. So if you go through one saddle point, it corresponds to a reconnection. If you think of a genus in a surface, like here's a torus, and here's the hole in the torus, and it's standing here, then I see that as I come near the top of the torus hole, I have a saddle point, and then I have another saddle point at the bottom of the torus hole. So that's two reconnections. Two reconnections form one genus for the surface. So then I can change my questioning to what is the least genus of a surface that bounds a knot in 4 dimensions. So we're sitting here in 3 space, and we're allowing the knots to evolve in time, and they can bound surfaces up in 4 space. And they will bound surfaces of various genus. Some knots will be non-trivial in 3 space, but they will bound a disk in 4 space. Mm-hmm. Others will have a least genus non-zero that they bound. If I had a knot that bounded a surface of genus 1, then I would not be able to reconnect it to the unknot in less than 1 reconnection, in less than 2 reconnections, because I have to, at the very least, create the hole in the surface, right? So I have that the genus is a lower bound for twice the reconnection number. So then we're over in the problem of what is the least genus of a surface that bounds the knot in 4 space, and that's just changing one problem for another. But it turns out that the Kauffman homology is able to make an estimate about the least genus of a surface in 4 space for a knot.
That was a very beautiful answer.
Thank you.
That was very nice.
Okay, good.
I have more
Other
basic
question.
What's the genus in 4 dimensions? I know what the genus of a surface means, but in 4 dimensions?
Well, it's still a surface, right?
Well, you have bumped into like one. I wouldn't call it a manifold.
I mean, a surface. If you have a surface, it exists independently. Mathematically, it exists independently of where it's embedded.
Yes.
And the way you and I are at the moment visualizing the genus of a surface, though, is we're thinking, well, how many holes does it have? And then you're thinking, well, I need to be in 3 space to see how many holes it has. But you don't actually have to be in 3 space at all, or any space. You're handed the data, which says that it's a locally Euclidean space, 2-dimensional, and it doesn't have any singularities. And then the genus is a topological characteristic of the surface. And your question is, how do we find out what it is? Well, one way is to build it. Let me show you by thinking of building it with some slide. We had a building picture here, right? So if you think about this, I started with the truffle knot, and I went through one reconnection, and then I went through another reconnection. And when I went through the first reconnection, I built a saddle. And then I'm going down, and I'm going down through these 2 components. And then the 2 components went through a saddle, and I end up here. So that in this case, the way I described the occurrence of the genus was that I went between one component to two components and back to one. And that's telling me that I got a genus. And that's still not going to be satisfying for you. So I have to find a way to define the genus that's independent of the visualization. Right? Now, there is a way to do that. I'm trying to think of a way to say this to you without bothering you with homology theory. Do you know Euler's formula for graphs in the plane? Euler's formula for graphs in the plane says that if you have a connected plane graph, then the vertices minus edges plus faces is equal to 2. There's a generalization of that. If you have an orientable surface and you have a graph drawn on the surface so that the regions are all, the interior of every region is a disk. So there's no interesting topology inside any region in the graph. You can draw graphs on a surface where there might be handles inside the regions. I don't want them. So I draw a graph sufficiently reticulated so that every region is a disk. And then the formula becomes vertices minus edges plus faces is equal to 2 minus 2g. G is the genus. So there's a formula for the genus in terms of drawing a graph on the surface that's sufficiently fine. And it will turn out to be exactly the number of holes when you visualize it in 3 space. Does that help?
Yeah, thank you.
Okay.
Yeah, translations are good. Yeah, thank you.
So that's what tends to happen in topology is you will start, it's really an interesting question. You start with something where you have a geometric intuition about it and you think, well, I know what it is, but then you realize I need to know it in a somewhat more abstract context, and then you have to find another way to define it.
Any other questions or comments from Zoom also? Okay.
I should mention that the physical side of this that I understand the least is what is going on when this reconnection happens. If you look at some movies that people have made, like there's a Russian Alexyenko in Novosibirsk who made some interesting movies of reconnection happening with vortices. You see that when the two vortices come together and are possibly going to reconnect, they do some very complicated things. They seem to send out sort of fibrils back and forth to one another, and all kinds of things are going on there. There should be a good fluid dynamics theory of the whole thing, but I think that there isn't at the present time.
Yeah. Basically, I wonder what's like the difference between Kelvin's statement and the fact that everything is made up by strings and not its strings. Anyway, yeah, I don't mean to be.
Well, right. I mean, if Kelvin's ideas were right, then you would have to think about all of this kind of complexity underlying the atoms. Perhaps you would. Perhaps you should. I don't know. Yeah. What we have done is we've decided on a kind of an abstract way to think about the micro world, and then slowly find out more, rather than make a hypothesis about the details of the micro world. Other questions? Okay, thank you very much.